Good. So we resume our story from yesterday. We ended up analyzing the two limits of the superpotential, either the cubic term vanishing or the mass term vanishing, and then we argued that in both of these limits, can you hear me, by the way? Is this working? Yes? I think so. Yes, okay. So in these two limits, we argued that the classical superpotential is the exact low energy effective superpotential also. So now we will consider the more complicated case of having both the mass and the cubic coupling to be non-zero. So now both in this kind of situation, both the U1R symmetry and the U1 flavor symmetry are spurious. Spurious means that they really are not symmetries of the action in the usual sense. They're symmetries in the sense of like you have to act on the couplings also to make the action invariant. Okay? And W effective, this low energy Wilsonian effective action, should be holomorphic function of the complex quantities m, y, and phi. And of course our job is to find this function. The other thing we know on supersymmetry is that the R charge of this quantity has to be 2. And the flavor charge has to be 0. Okay? Otherwise we will not have supersymmetry. So this turns out to be very constraining. So the only combination you can form, which is holomorphic and R charge 2 and flavor charge 0, is this one. This one has automatically NQ flavor equal to 0. You can check this using the table I had on the board yesterday, which one of you corrected the mistake in it, so you've been following that. And then there's this quantity that I emphasized already in the table, which is holomorphic. This is the unique holomorphic combination you can form from these quantities m, y, and phi, which has R charge 0 and flavor charge 0. Okay? So with this at hand, you automatically know that your low energy effective superpotential has to be of the form okay? So you've reduced the problem to looking for a function of one variable that has to be holomorphic. That's your job. And now, of course, we know this function in the two limits that we studied. So if y is equal to 0, we argued that this effective superpotential is just the mass term. So in this language, you have that f of 0 is equal to 1. And when m goes to 0, we have this answer. So you know that the behavior of the holomorphic function at 0 and asymptotically on the complex plane for any complex value of u, it has to be 2u over 3. This function, when converted into this language, this answer, when expressed in this language, leads to this function. So now, those of you who know complex analysis well can already anticipate that these constraints are very, very restrictive. So in complex analysis, if you have a holomorphic function with prescribed behaviors at some points, especially at infinity, this almost always fixes the function. Or often fixes the function, okay? Good. So now it's still not, we're still not done, because, for instance, there could be some behavior here between 1 and at infinity, that between 0 and infinity, that is somehow interpolating between these two. So we still have to do a little bit of work. So I have both of the couplings non-zero. So I can go in the limit of small coupling, meaning small u. You see, the coupling that induces interactions is y. So when y is small, u is small. So in that limit, you can do Feynman diagrams. Loops, let's say. And then there's a somewhat quick, but I think good enough argument in Strassler's lecture notes that tells you basically that so when you do loops, you would expect in general that you will induce terms like phi to the power k when k is bigger than 3. You will introduce, in general, higher powers of the field phi. But what happens is that these things, when you start computing loops, even without computing the detailed coefficient of the Feynman diagram, the structure of the loop interactions of the the vertices and the fact that these are complex numbers will you can show that the coefficients here are of the type y to some power, but then you need a power of this, of the modulus of y. And then some coefficients. So you don't even have to compute the coefficients to see that this structure is not holomorphic, so it's not allowed. This is the power of holomorphy, as was called by Seiberg. So you don't actually have to compute the Feynman diagrams. You can sit down and compute them if you want to and see that these vanish, but they're guaranteed to vanish because of this. So there's some example of loops in the lecture notes by Strassler where you can really sit down, you can see from the Feynman diagram that this will be the structure, and then convince yourself that this cannot be holomorphic. So this argumentation leads immediately to the fact that to all orders in perturbation theory, W effective is equal to W classical. Okay? So this is already a powerful statement, but it is actually, we can do better than that. We can ask, what about non-perturbative effects? Non-perturbative effects are, if you have a coupling lambda, a non-perturbative effect is something like this, lambda to some power, positive power. Because this function can never have a Taylor series expansion that will give you a Feynman diagram. So this is, strictly speaking, a non-perturbative effect. It's like instantons behave like that. Good, so when lambda is small, you completely miss these effects, but when lambda is order 1, these are important contributions. So in principle, we should worry about effects here of the type e to the minus 1 over u to some power. Okay, so just to sum up, so far we have used these two limits as well as Feynman diagram arguments to argue that to all order in the loop expansion, let's call it like this, W loop is 1 plus, m phi square over 2, and then 1 plus 2u over 3. So the function f has this form up to corrections like this. Okay? So now we have to argue, well, we don't have to, but it's true, that corrections like this are going to vanish. So this is the full answer, is the claim. So how do you do that? Well, you have a function where in the neighborhood of 1, so that's what this loop analysis gave us, in a finite neighborhood around 0, the function is a constant. And then it has a prescribed behavior at infinity, which is 2u over 3. So you have to prove that this is the unique function that is holomorphic and does that. So for instance, you can imagine, so f of u is 1 plus 2u over 3 plus something else. You can try to convince yourself that this has to vanish. So for instance, you can start writing things like this. This is certainly compatible with the behavior at infinity and at 1, at 0, but this is not a holomorphic function. And so you can also say, okay, but what about this function? This is holomorphic, and at infinity will be fine, but for small imaginary u, so when u is around 0 in this limit, but imaginary, so in the regime of validity of the Feynman diagrams, this term, if you add it here, it will spoil the behavior around 0. And so this is also not allowed. And okay, I think you can probably devise a proof that this has to vanish, some more formal proof. But this type of arguments from complex analysis will inform you that this is the full answer. As I said, the same result can be obtained using, let's say, more computationally intensive tools like supergraphs and, Feynman diagrams in superspace, if you wish. But then you still have to worry about this non-perturbative effect. So you would need an argument like this from holomorphicity to show that there's 0. All right, so we have a bottom line, which is that the full effective superpotential, the full quantum thing, is m over 2 phi square plus y over 3 phi cubed. So no renormalization is allowed of the superpotential. Okay? This is the result. And in fact, this is okay, we have analyzed this in some detail in this simple model of a chiral superfield with a cubic superpotential, but the statement is much more general. With this amount of supersymmetry, meaning 4 real supercharges, in 2 dimensions, in 3 dimensions, in 4 dimensions, you always have this kind of what are called non-renormalization theorems. You have a statement that the classical superpotential that you write down will not be affected by quantum effects. Or, to be more precise, it can be affected up to 1 loop. So here, at 1 loop, we didn't see a modification, but if you have a gauge field in the game, or some more complicated interactions, there could be 1 loop effects. That's it. So these are very powerful statements that allow you to fix a lot of the quantum dynamics of a theory simply by relying on this holomorphic behavior. So this is not an accident for this model, is my point. It's a general feature due to this holomorphic structure of the superpotential. So Are there questions online, or I heard something?
Can you hear me?
So, for instance, when Seiberg and Witten studied the low energy behavior of 4-dimensional n equals to 2 non-abelian gauge theories on the Coulomb branch, so when you have certain expectation values for the scalar fields, they used arguments like this, quite a bit more sophisticated, to essentially fix the low energy effective superpotential and so solve the theory on this branch of the vacuum moduli space.
Can you hear me? Hello.
Yes, can you? I don't hear well.
Can you hear me now?
Yes, I can.
Yeah, all right. Does this mean that these theories are UV complete?
Very good. So, whether the theory is UV complete is, well, in this example, it is because the beta function, well, I still haven't talked about a beta function, I also do, but yes, these are asymptotically free theories, so they're free in the UV, so yes, well behaved. The general holomorphic argument applies also to non-renormalizable theories. So in that sense, you don't need renormalizability to use these arguments about holomorphicity. But in these examples that I mentioned, we do have UV complete quantum field theories. Is this a good answer?
I see.
Yeah.
Yeah, thank you.
All right. So now at this point we come to something that I mentioned yesterday. You may think that this is a very boring theory, nothing quantum happens. It's just the classical theory is the full answer. But that's wrong. The reason it's wrong is that, so the naive outcome of this may be like, oh, the couplings do not run, nothing's renormalized, nothing changes as I vary the energy scale, but that's wrong. And the reason it's wrong is the fact that I also have another function in my classical Lagrangian, which is the Kähler potential. So the Kähler potential is not holomorphic. And so this simple observation leads to a possible renormalization. But it's a very mild form of renormalization, which we will study now. So the Kähler potential K in this example is a function, a real function of these quantities. And so, of course, when you don't have holomorphicity, the functions are much less constrained. So, how do we reconcile these two things about the couplings? On one hand, from the superpotential, it sounds like the couplings don't change, but here I'm saying that they may change. Well, the reason has to do with the fact that the couplings that appear in the superpotential are not the physical couplings. They're not really the things that appear in endpoint functions or scattering amplitudes. So from now on, I'll call the couplings in the superpotential, I'll call them the cubic one, I'll call it y hat. So the superpotential will have a term. Sorry. The reason I'll be doing this is that we talked about it a little bit yesterday. If you rescale the field phi by some constant a, well, this rescaling of the field will change the Kähler potential. Okay, because the Kähler potential will have to go to a square phi, right, under this rescaling. So this is already an indication that something can happen. So this, of course, is an artificial rescaling, but you can phrase it in the language of renormalization as in the following way. K, phi dagger phi, in our example, it starts its life as a simple function in the classical theory, like that. But there could be what's called wave function renormalization. So when you studied quantum field theory, you learned that the couplings get renormalized, but also the fields themselves get renormalized, right? So usually these wave function renormalization factors are called Z. There's many Z's here, but this Z means the renormalization of the field phi or the Kähler potential. So if you rescale like this, y hat rescales like this, and z rescales like this. So again, these are artificial rescalings that I'm doing by hand, but they are supposed to instruct me what can get changed when I do an RG flow. So the invariant coupling is, so a useful notion to define is this coupling. It's y hat complex conjugated 1 over z cubed y hat. So this coupling can run. So y can run, get renormalized. So basically the point is that y hat, as we saw, does not change. So it's an, if you wish, it's a non-physical but a holomorphic coupling, so it doesn't change. But y, this y, the non-holomorphic one, this is not, nothing constrains that the dependence of the low energy effective action has to be holomorphic in y. So this one is the physical one that runs, but it's not holomorphic. Okay? So this is the only type of renormalization that can happen in this model. This is very, if you wish, mild thing that can happen. Usually in quantum field theory, when you don't have supersymmetry, for every coupling that you write down, so here I have cubic, just to remind you, I have kinetic terms, I have whatever, same for fermions, I have Yukawas, I have phi to the fourth interactions. So that's the schematic form. So in ordinary non-supersymmetric quantum field theory, I can get independent renormalizations for the field phi, the field psi, so two types of wave function renormalizations. And then for the cubic term and for the quartic term, I also get two couplings that run. So I have to compute, if you wish, 4 different renormalized quantities. 2 for the wave functions and 2 for the couplings. Because of the magic of supersymmetry, now I have to compute 1, this one. So these 4 different renormalizations have combined into just one thing I have to worry about. That's really the crucial point of supersymmetry. It really constrains what can change in the quantum dynamics. Okay. Good. So now, at some point, one has to do some calculations, right? I cannot keep on getting physics for free. So this is the time, but of course I will not do them in front of you too much. But the calculations are kind of, well, at least in this model, the calculations are basically simple quantum field theory with scalars and spin 1/2 fermions. which you hopefully have seen in some course on quantum field theory. Okay, so to kind of illustrate what happens, let's fix for concreteness d equals 4, n equals 1, and do perturbation theory. Okay? So the perturbation theory that you have to do is to find how is this quantity z, the wave function renormalization, you have to compute it, right, by doing loops in the usual way. So z will depend on the energy scale mu, and we'll do one loop. And roughly speaking, you have to worry about, at one loop, you have two types of diagrams. Let me write it like this. And then you have, so the different lines, so this is the two-point function of phi. Why the two-point function of phi? Well, that's the kinetic term, right? It has two phi's. So this diagram will exactly contribute to the renormalization here. And then this one. So what are these vertices? So this cubic vertex here is between phi and f. And this one is between phi and psi. So this is the Yukawa coupling, and this is this funny coupling between the auxiliary field and f. You can rephrase this one as a quartic vertex of phi with itself. So if you start having moral ambiguities in your head, wait a minute, what is a propagator for a field without a kinetic term? You can be a bit more sophisticated and study this diagram instead of this one. So this will be phi, 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 and a quartic vertex. So this is the usual phi to the fourth vertex, okay? So anyway, the result will be the same. Okay, so I have to compute these two diagrams, which I will not do, but you have to compute them. I mean, these are really simple integrals that are in every quantum field theory book, right? With these two. So hopefully, how many of you have seen this type of on-loop diagrams? Okay, so almost everyone. Good. So you do that, and you find that the answer is, so this is inspired by the Strassler lecture notes, where he's not even computing that. He's just like arguing for the sign of the coefficient. This is the American style of doing physics, to kind of be lazy until the very end of the calculation. So I will follow that. But you already see something interesting here, something that I already told you. Is that, so this is an order 1 number, something like whatever, pi squared, something like this. So this is the thing that you have to compute from these loop integrals. There's a log term because you're in 4 dimensions. This log is due to the fact that the lambda phi to the 4th coupling is classically marginal. You don't get a power of the cutoff scale lambda uv, you get a log of the cutoff scale. And then this is kind of the thing I was emphasizing before, is that loops will give you not a holomorphic function in front, it will give you the modulus of y. All right, and this C0 is something order 1. It will not be an important number for us, except that it has to have a specific sign, and it does, and we'll argue what the sign is in 2 minutes. Okay, so now we can study the beta function, meaning how does the coupling, this is the guy that's going to run, right? Not y hat didn't run, it was holomorphic, but this one can change. And so the beta function, you can define many beta functions. So the beta function of y squared can be defined in terms of beta functions of y and y star. Y star is the complex conjugate. Is -3 y squared d log z d log mu. I'm not sure why this -3 is in the game, but I mean, why this 3 is in the game. But anyway. So this renormalization of the field leads to the renormalization of the coupling. Yes. So now you also can define the anomalous dimension of the field, define gamma mu minus d. This is the usual thing because you renormalize the field. This z does exactly that, and so the scaling dimension of the field is going to change with energy scale. So this is what's called anomalous dimension. Of the field phi. One aspect of supersymmetry is that the anomalous dimension is a property of the whole superfield. The reason is that the scalar, the fermion, and the auxiliary field are related by an action of the supercharge, and the dimension, the scaling dimension of the supercharge is fixed to be 1/2. And so that's why I'm writing it like this. So if you look at the scalar phi, the classical dimension is 1. Scaling dimension, I'm in 4D. The general formula was d minus 2 over 2 for the scaling dimension. And then I get a correction, which is this. And this is what's encoded here. Okay. One thing that is crucial and the essence of the story is that these two are controlled by the same function. This is again what I was emphasizing before. So in usual quantum field theory, without supersymmetry, these are independent functions. They can flow independently. But here, they don't. And so you have a relation, beta y mu is 3/2 y gamma of mu. This is exact, is the claim. This exactness has to do with the fact, again, that the superpotential is not renormalized. So this doesn't depend on Feynman diagrams or loop approximations or anything like that. This is a non-perturbative statement. Okay, good. So now I have this, I've computed this from these two Feynman diagrams, or I could have computed it if I wanted to. And this is the function z that controls how, perturbatively at least, how these functions evolve, the beta function and the anomalous dimension. So you find that gamma, approximately at one loop, is this C0 tilde. I don't know why there's a tilde there, but anyway, it's like this. Okay? Beta of y is minus 3/2 C0 y square. So these are the one loop results, right? That's why it's approximate. And of course, as advertised over here, they're related by this exact relation, which persists at all loops. So now, at this point, it's crucial to compute C0 tilde, right? Because that will inform you how this theory behaves as a function. Is it asymptotically free? Is it, conformal? Is it, so if C0 is equal to 0, for instance, this will be a vanishing beta function. It will indicate a scalar invariant model. And so you can sit down and compute C0, or you can be lazy. And Strassler is lazy. You should remember that this was a lower bound. This was this unitarity bound for a scalar field, for the conformal dimension of a scalar field. So delta is greater or equal to d minus 2 over 2 is a bound from unitarity. And you see what gamma is doing here. So this argument suggests that gamma can only increase the dimension because you already have you're already at the bound, and you have a correction from some loops, and they should only increase it, not decrease it. So this fixes the sign of C0, which is really what you want. So C0 tilde is less than 0. This is the argument. Okay, so now you've learned something. You've learned this sign, which gives you the sign of the beta function. So you find that beta of y is greater than 0. This means that the theory is infrared free. So at low energies, this coupling y, which is the only interaction in the theory, controls the interactions. So, I mean, of course, if y vanishes, I have a free theory, so gamma vanishes and nothing interesting happens. The beta function vanishes, but it's a free CFT. So when you turn on y, you're asking what happens at low energies, and this instructs you that nothing happens. So the theory is just infrared. This interaction doesn't survive at low energies. And so the theory is infrared free. And what happens in the UV is a good question. It has to be studied, but maybe it's not UV defined well and so on. But it's infrared free. Okay. So this is actually not really, this last fact is not really something that it depends on supersymmetry or the number of scalars and fermions. It's this general statement that I told you, which is that in 4 dimensions, remember, we're in 4D spacetime, you cannot write down a interacting theory of scalars and spin 1/2 fermions. You need gauge fields to have an interacting quantum field theory at low energies. All right. So the conclusion here is that this Wess-Zumino model and every other model with only spin 0 and spin 1 particles, spin 1/2 particles, is boring at low energies. It's a free theory. Another way to say this is that the coupling y is marginally irrelevant. So classically, it looks like lambda phi to the 4th. This interaction is marginal, right? It's a dimensionless coupling, and also this one, the Yukawa term, but this one-loop analysis suggests that the beta function is a positive, which means that it's marginally irrelevant. So it's eventually irrelevant. And it's essentially due to this log and the sign of the log. There's fancy names for this, dimensional transmutation and all that kind of stuff. But it's really this sign. Any questions about this? Yes? Right, right. So you're saying, what if it's exactly 0, right? If it's exactly 0, well, then at least at one loop, you have an indication that you have a conformal theory. So you have to go to 2 loops to check. This is like a general feature of classically marginal operators or couplings, is that, I mean, if you do a perturbative analysis, you cannot really prove that it's exactly marginal. You have to, you should always expect that if something is 0, there should be a good reason for it to remain exactly 0. So yes, but if you want, in this example, these 2 diagrams are really in the books, and you can really find out what the answer is. So that's probably the most convincing. So here, a laziness prevails, but it should not. Yeah, so you're right, absolutely, that one should compute stuff. Yeah. But identical argument, I mean, this is really not a feature of supersymmetry, as I said. You can really start from lambda phi to the 4th without even the fermions and show that lambda phi to the 4th leads to boring infrared physics. There's many ways to say this. The four-dimensional Ising model is boring. It's a free theory. It's all the same statements. Where was I? Yes, I was in 4 dimensions, but now I'm going to go to 3, and things will become sufficiently, well, drastically more interesting. Please. Some interesting what? Yeah. Specifically for this model, I don't know, but in general, there's a whole field of, statistical mechanics oriented, where, well, what is non-unitary stuff? You have to lose energy. So everything that has dissipation, every low energy effective physics that has dissipation, viscosity, all kinds of, the real world is non-unitary, right? Appears to be non-unitary. This is a deep fact of life that I personally don't know. I'm on the record, so I can be fired, but I don't know why it happens, right? You start from some fundamental. Let's not do quantum field theory, right? Let's do quantum mechanics. And you fool yourself that you understand the fundamental theory, right? Whatever Dirac and Schrodinger and all the giants told you what to do. Start with the Hamiltonian, and in principle, even if you have 1,000 electrons or 1 million electrons, this is some complicated quantum many-body system, and this thing is unitary by construction, right? The Hamiltonian is self-adjoint, the spectrum's real, blah, blah, blah. Discrete, gapped, everything's fine. And then out of this fundamental structure, you should explain that when you drop a ball in a pot of honey, it goes slower to the bottom than when you drop it in a pot of water, right? Explain that from the Hamiltonian of 10 to the 23 molecules, right? And yeah, so you lose energy somehow, but this is some kind of collective phenomena that arises because of thermal fluctuations and so on. So it's a complicated thing, and it is worth to ask, are there critical systems in nature that are, non-unitary? So is this unitarity assumption? It clearly appears to be a fundamental property of quantum mechanics, but if you don't care about this, and if you just want to somehow describe some relevant collective degrees of freedom in some condensed matter system, not all the details of the microscopics, but the emergent low energy behavior, it could be non-unitary, and in some sense, generically, it's not unitary. And so then you should study non-unitary critical systems, and that's a big field of study that I'm no expert on. So, for instance, I know that if you start studying, you start dropping sand and make a pile of sand, at some point you have self-similar behavior because things starting, so there's some structure that emerges. Then when you start dropping the next sand, piece of sand, then it slides in a specific way. So this kind of criticality or self-organized behavior, self-similar behavior, it's not unitary, but it's a scale invariant in some sense. So you still have polynomial decay of fluctuations instead of exponential, and it's very interesting. I'm not sure I answered, but yeah. So in the context here, we pretend that these are models relevant for some fundamental aspect of the interactions and not emergent. But Actually, I'll make a comment that these are actually also models of emergent phenomena in condensed matter. So, yeah. If you want to read more about something that's not really too far away from, let's say, particle physics or fundamental interaction physics, you can go and Google the Yang-Lee model in 2 dimensions. So there's a very well-known 2-dimensional CFT that's non-unitary. It's exactly solvable, meaning you can find all the critical exponents, all the endpoint function. It's interactive, so strongly coupled. It's not a Gaussian theory. And it's, it finds applications in some statistical mechanical models. Yeah, I think it's really important to, so probably most of you have some background or aspirations to do high energy theoretical physics. You should just be aware that it's much better to have aspirations to do physics. Because, I mean, it's much more beautiful than to put a bunch of adjectives in front. Okay? Good. After this sermon, let me go to 3 dimensions. So now, the coupling Y is dimension full. So in 4 dimensions, it was dimensionless classically, and I got this log, and so on. But in 3 dimensions, Y is, so the dimension of Y, the scaling dimension is 1/2. Okay? So I already have a scale in the problem, so this cannot be a conformal theory, at least in the UV, where I write down the Lagrangian. So I'm going to define a new coupling. So omega is a scale invariant by construction. So mu is some energy scale at which I observe the physics. And this now is dimensionless. And makes manifest the expectation that as you dial mu to infinity, meaning you're in the UV, the theory should be free. So the coupling vanishes, this coupling. As you go to the infrared, when mu goes to 0, this blows up, so there should be some kind of strongly coupled physics kicking in at some point. So this is also an indication that you can do perturbation theory close to the UV, meaning at high energies, but at low energies, we should not be doing perturbation theory. Okay, so you can then really repeat the whole story of the renormalization of Z and the beta functions and really do the same thing, but now there will be various factors of this 1/2 appearing as additive factors just to take care of the dimensions. And if you do this, you find, just like we computed the beta function of Y in 4 dimensions, it's the same 2 diagrams or the same analysis that will give you this answer. So this is the exact answer. You find an exact relation between the beta function that controls how the coupling changes with energy scale and the anomalous dimension of the field, of the fields, because I have bosons and fermions. So this is exact. Of course, if you are close to the UV when omega is small, you can do perturbation theory, and you can find that this is small. Okay? So I'm not even computing any coefficient here. This is just counting the vertices of the loops, of the 2 loops, and see that you have omega squared. It's exactly the same y squared that we saw in 4 dimensions. So the dimension of phi is 1/2 plus 1/2 gamma. So the only thing that has changed is that before in 4 dimensions I had 1 here, but I told you that the general formula is d minus 2 over 2. So d is equal to 3 now, and so have 1/2, and then some correction to that. So this comes from one loop. So, and this is small. So what you learn from this analysis is that the beta function in the UV at high energy, beta as mu is much bigger than 1, so mu goes to infinity, beta function is, well, I have something that has to be positive, because if the coupling is negative, I have issues with stability of the potential. So this is positive, and then have minus 1/2 plus a small number. So the beta function is negative. Okay? Negative beta functions have a name, asymptotic freedom, right? So whenever you have a negative beta function, it means that the theory is free at high energies. Meaning the coupling is not relevant at high energies. It's not important. It's relevant at low energies. Okay. So we learned that when this coupling is small, beta is negative. Good. What's important here is that now I have exact relations like this. So the coupling starts off with a negative beta function, and gamma is going to grow. Actually, you can compute the sign here. And you see that this in perturbation theory will be a positive number. And so you could wonder, when will this flowing of the coupling stop? It will stop if gamma hits 1/3. So if this anomalous dimension becomes 1/3 at some value omega star, then the beta function is going to be exactly 0. Beta functions equal to 0 mean we have a CFT. We have a scale invariant quantum field theory, and so notice that this is order 1 number, and it can only happen when the coupling is large. It's order 1. It cannot happen at small values of the coupling, because we know the behavior at small values of the coupling. It's gamma is approximately 0. And so, so this is beyond the reach of perturbation theory. Beyond perturbation theory. So, at this point, I don't have a proof that this will happen, but let's assume it happens. Okay. Yes. So then you have this picture that emerges, this plausible picture that emerges about this story. Is that this RG flow has this kind of 3 regions, if you wish. So I have a single coupling, which should change with scale smoothly. This is an expectation we have. And so basically what happens is this simple RG flow. You start in the UV, the coupling vanishes, you flow. This is the direction of the flow, so you lower the energy, and you hit some point omega star, and then you have, in principle, you can continue in coupling space. But what happens is at this point, the beta function vanishes, so if you're on the right-hand side of the point, the direction of the flow is going to change. This is what fixed points of differential equations do. They can be either attractive or repelling fixed points. This is from elementary theory of differential equations, because the beta function is a differential equation, right? It has mu d of the coupling d mu. And I'm studying how the flow of the coupling behaves, and I learn that there is a fixed point. And it's an attractive fixed point. So the sign, the direction of the arrows is controlled by the sign of the beta function. So, no matter what, if I have such a fixed point at some finite value of omega star, it will control the low energy behavior. So this CFT controls the IR behavior. This is the story. Okay. So at this point, again, I'm emphasizing I haven't proven to you that there's a CFT. And in fact, I claim no one can prove that for you at the moment, not forever, but as far as we know, with the methods we know, I don't know how to make a proof of this, if you wish, simply because we don't understand the path integral of quantum field theory. But this perturbative analysis and this exactness of the beta function suggests that this is something that could happen. And again, let's assume it happens and see how much we can learn about this putative, strongly coupled conformal field theory. Well, you find immediately that the dimension of phi. This is the power of supersymmetry for you. Because gamma is 1/3, I put it in this formula, and I do simple math, and I find that the conformal dimension of the scalar operator phi, this is a non-perturbative statement, right? This is, and beyond perturbation theory, these are order 1 numbers, it's exactly 2/3. And then at this point, you go back to your notes from Monday and recall that, well, first of all, go back to yesterday and recall that the R charge of phi is 2/3. And then you observe that 2/3 is equal to 2/3. And then you recall that the general statement of chiral primary operators in 3-dimensional n equals to 2 CFTs was this. So this perturbative analysis plus the plausibility assumptions connects precisely with the algebraic analysis of the superconformal algebra in its representation theory. So if such a CFT exists, it's a 3-dimensional n equals to 2 CFT, and this operator phi is a chiral primary operator. It's this LB1 bar multiplet that I talked about. Okay. All right. And in general, as I mentioned, you can, the general story is that it's d minus 1 over 2 QR. So this is valid in 2 and in 4 dimensions. You can reasonably say, wait a minute. In 4 dimensions, you told us that the theory is boring. This equation knows about that, because if you put 2/3 here, so if I haven't messed up, yeah, I haven't. If you put 2/3 here for the R charge, which is the same for every value of the dimension of space-time, and if you put 4 here, you find that the dimension of phi is 1, which saturates the unitarity bound, which means it's a free field. The unitarity bound in 3 dimensions is 1/2, and 2/3 is notably bigger than 1/2, so this is not a free field. This is another way to see that this CFT is not a free CFT, it's an interacting CFT. And in 2 dimensions, you'll get, it will be actually an interacting CFT also. Yes? Good point, yes. I'm assuming at the moment that the mass I've tuned to 0. I'll have more comments on this, but the comments I already made yesterday. If you are to ever find a CFT, this is a general QFT statement, you have to tune a relevant coupling to 0. the parameter m in the Lagrangian is equal to 0. Very good. So then you can say, I have read in books that Feynman diagrams and quantum effects can induce couplings that I've tuned to 0 in the classical Lagrangian. What happens here? What happens is that the coupling m square phi square breaks the U1R symmetry. And so when you do renormalization, you can induce couplings that are compatible with the global symmetries that you start with. So m square is, if you tune it initially to 0, if you don't break the U1R symmetry by hand, it will not be generated by Feynman diagrams.
So it's a bit different from the standard, let's say, lambda phi equal to 3 dimensions.
Correct statement, yes. It is, again, the power of supersymmetry that guarantees for me that this will not be an induced coupling if I tune it to 0. So the tuning is much smaller than, if you wish, lambda phi to the 4th.
If I'm not wrong, in that case, you have to use the critical mass to be 0, but the parameter in the Lagrange will not be 0.
Correct.
In this case, both are 0.
Yes. In this case, both are 0 because of this extra U1R symmetry, yes. So indeed, this is an important thing that I'm sweeping under the rug, but now I'm not because you pointed it out. Yes. So this is totally obeying all the rules of Wilson, Polakov, Kadonov. There's no mumbo jumbo here, except that I just have a lot of extra symmetry, which really constrains what the RG can do. So supersymmetry is not some exotic thing. Okay. When should I stop, Davide? At 1? Or 5 minutes to 1 or something like this? All right. So at this point, we've done what we can, roughly. And there's a conjecture. So of course, in the modern era, scientists should have conjectures, otherwise it's boring just to compute stuff, right? You have to conjecture stuff so that other people can compute and then cite you. That's the algorithm. So here's the conjecture. Unfortunately, I didn't do this on time, so it's a kind of a boring thing. There is a three-dimensional n equals to 2 superconformal field theory arising in the IR of the Wess-Zumino model, which is strongly coupled, and which I will call the critical Wess-Zumino model. This thing exists, is the conjecture. How can we prove this? Well, as far as I know, we cannot prove it. It's roughly speaking in the same spirit as the conjecture that lambda phi to the 4th in 3 dimensions undergoes an RG flow that ends at the Ising critical point. The critical point in the universality class of the Ising model. That is still a conjecture. No one has proven it, but we have overwhelming evidence. Experimental and also calculational evidence, but there's no proof. So in the same spirit here, we can ask, how can we convince ourselves that this is not wrong? So the evidence for this claim, as far as I know, can be split into, well, there's really 3 lines of attack here that I know of. The first one is this ingenious idea of Wilson and Fisher to study quantum field theory in 3.99 dimensions. Okay, this is how the paper is called. So I was emphasizing, some of the formulae here. D is a parameter. So you can study this formally, this quantum field theory, in an arbitrary number of dimensions that are not integer. What this means, I'm not going to address the philosophical implications. You just sit down and compute. It seems to work. If epsilon is small, So if you are in 3.99 dimensions, uh, you can actually, so roughly speaking, this omega square, this omega star is going to move closer to 0. So the distance between these points is roughly speaking order epsilon or epsilon square, I'm forgetting. But it's controlled by the dimension. So here it's order 1 because we're in 3 dimensions, but if you're in 3.99, it will be a small parameter. So, you know, physicists can only solve with the harmonic oscillator. That's roughly a true statement. So you desperately look for a harmonic oscillator in every calculation that you do. And they were smart enough to find one. So then once you have epsilon small, you do the harmonic oscillator. The magical thing that happens, so if this will work in 3.99 dimensions, okay? And the magical thing that happens is that you don't put epsilon to be 0.01. You keep epsilon explicit in your calculations. And when you're done, you put epsilon to 1. So you violate all rules of mathematics, and you get a result that matches experiment within 1% or something. Because we have experiments, right? We have the Ising model realized in some whatever, boiling liquids and stuff. And at this point, you say, okay, I have no idea why this works, but it works. Roughly speaking, we still don't have a very sophisticated idea why it works. Okay. The second idea is again the same idea, find a harmonic oscillator. So instead of one chiral superfield or one scalar field, so these two ideas are exactly the same without supersymmetry. They were invented just for lambda of I to the 4th. You have n fields that go from 1 to n. And so in our context, the Lagrangian will be y. Sum I from 1 to n, phi I cubed. Okay, so now you could ask, what is the small parameter here? Well, I have an integer n. I can take that small, large. So you can show that the location of this point in this model, this one, by the way, is called the ON model, because these interactions will be invariant under rotations between the n fields that you have. So there is an ON global symmetry here. And so the ON model at large n has a perturbation theory in 1 over n. So you can go back to doing Feynman diagrams. Okay, so these two tools are, how to say, have been around for almost 50 years and have been used for many, many models like this, with supersymmetry, without supersymmetry, various configurations of scalars and fermions and so on. So these are well-known tools. There's also new tools. And so I'm going to mention 2 of them that are relevant in this context. The first one I already mentioned is the conformal bootstrap, or at least the modern incarnation of the conformal bootstrap is this idea. Let's assume that there is a CFT, and then use the full power of the conformal symmetry. For instance, these conditions on the 4-point functions, this crossing symmetry. This schematic equation constrains the possible CFTs. And so you can start exploring this numerically and then put bounds. And then if you're lucky, your bounds will have some special feature. And if you zoom in on the special feature, you'll find interesting CFTs living there on the border, if you wish, between the allowed region and the disallowed region in the space of possible conformal dimensions, for instance. This magically works again, for the non-supersymmetric Ising model, that was the first example that was analyzed with these methods. And again, as far as I know, we don't understand why it works. But again, you'll get lucky and you identify, so this is a non-perturbative scheme, so there's no harmonic oscillator here, but you don't solve the problem, you put bounds on the problem. So it's a numerical approximation scheme. And then another tool that we know is called supersymmetric localization. This tool obviously requires also supersymmetry. And so this is a very powerful tool for computing certain observables only. And it's also an exact result. So it's really not a harmonic oscillator, although the details of the calculation, there is a harmonic oscillator. It's always like that. Good. So in the rest of the lecture today and also tomorrow, I'm going to talk about these three methods, 1, 3, and 4. I'm not going to talk about 2 because time is finite. Okay, so let's start with arguably, I think, the most ingenious of the methods and somehow the easiest to understand. This is called the Epsilon Expansion. How many of you have seen the Epsilon Expansion? Oh my goodness, so you'll all be bored. But really in this lambda 5 to the 4 context? Okay, so, okay. Well, anyway. I will quickly review what happens with the Epsilon Expansion. So we start in 3.99 dimensions. This is Wilson and Fisher, 1974. And just to keep things very simple, I'll start with the lambda 5 to the 4th model. So again, there's no mass term. Okay, so here I have only one interaction. Sorry, not squared, fourth. One interaction vertex. So at 2 loops, at 1 loop for the 2-point function, I have only one diagram to think about. This one. So I have to compute this. 1 loop 2-point function. 1 loop 4-point. I have to worry only about this guy. Okay, so this is what you have to compute. And one thing that you may have seen is that these kind of quantum field theories can be studied in what's called dimensional regularization. Okay? So if you really are fixated on 4 dimensions, you move away D a little bit away from 4 with a parameter epsilon. So epsilon is 4 minus D. You compute the divergences associated with these diagrams. There will be 1 over epsilon to the power 1, to the power 2, and so on. And these are going to be the divergent terms that you then subtract when you take epsilon going to 0, if you're interested in computing things in the standard model, for instance. This is a well-known regularization scheme. Here, what they did is not that. They fix, it's the same analysis of the diagrams, but the perspective is different. So you do epsilon small, you compute loops, and you find that the beta function is like that. Okay? But and then there's, of course, order lambda cubed, epsilon lambda square, and so on. So at 1 loop, you find this answer. And then, if you're doing 4D physics, you will put epsilon to 0. The beta function will be positive. So this is actually the number that I was, this is what I called C0 tilde an hour ago. Okay? And so you find a positive beta function in 4 dimensions, so this model is IR-free. That's the lesson. But instead of this, you ask when is beta of lambda equal to 0? You change the question, and the calculation is the same. You find that if lambda is 16 pi square over 3 times epsilon, you know, 2 approximately, right? Because I'm doing only one loop here. You find a fixed point, meaning that the beta function is 0. So you find a CFT for this value of lambda. So you immediately learn that if d is greater than 4, lambda, sorry, this should be lambda square. Yes, something's wrong. No, I'm sorry. Lambda itself. I have a lambda here. Sorry. So lambda is negative, right, at this fixed point. So for instance, if you are in 4.01 of dimension, you will have a fixed point, but the value of lambda will be negative, and then the potential will be unbounded below, which we call unstable. Right? But if you're in less than 4 dimensions, lambda will be positive, and moreover, lambda will be small. So you have a, and the coupling is small. So you have a perturbative CFT, meaning that you can compute observables in this CFT doing perturbation theory. And this is really the observation of Wilson and Fisher. So we can compute those observables, again by doing essentially the type of Feynman diagrams that are here on the board, and you can do 2 loops and so on. So for instance, the dimension of phi is d minus 2 over 2 plus 1/2, like, okay, eta. So this eta, I'm sorry, I took it from another source. Eta is a standard thing in statistical mechanics. I will explain what it is. So if you have in statistical physics, you have a correlation length, and this nu is called a critical exponent. So the correlation length diverges when you have a critical point, when you have a scale invariant system, but it diverges in a power law way controlled by this quantity, and the power is something that you can measure in the lab. And this power is related to the dimension of phi in this way. So there's some translations between going from statistical mechanics language, where these critical exponents were defined 80 years ago, and quantum field theory language. But ultimately, the dimension of the field is related to the critical exponent through this chain of redefinition. Anyway, this guy you can compute, and it's equal to this. Okay? And of course, this is to leading order in epsilon. There will be a whole series in epsilon, which, just as in usual quantum field theory, Friedman-Dyson told us that this perturbative expansion in QFT is not a convergent series, it's an asymptotic series. So here, even if you compute 300 loops, which you cannot do, but even if you do it, this will not get you closer to the answer. So we should live with that, or be very brave. Take this number, this quantity, only this one loop, and put d equal to 3 or epsilon equal to 1. Put it back here, and you find that delta is 0.5182. Okay? Then, sorry, I This is, sorry. This is the, this quantity, let's call it experimental or Monte Carlo simulations. Sorry. You believe that this leads to the Ising model in 3 dimensions, to the critical Ising model. You can study that model by using completely different methods from statistical mechanics, where you have a Hamiltonian with spins up and down and interactions, and then put this on a computer and try to tune your system to the critical value and try to extract the correlation length. Or go and measure in the lab. I think in the lab you can go up to 3 digits or something like this. But anyway, these are independent results obtained by other methods. And then if you do this, in our simple approximation, you get delta is so, you know, you'll get a pretty good approximation already at 1 loop. If you do 2 loops, you get epsilon cubed, correction to eta, which I didn't write down, but I wrote down what delta is. So this starts looking like something very nice. It's very, very close to the independently obtained answer. If you do 1 more loop, it's going to get worse, and so on. So it's not a precise science, but it's a curious observation that this epsilon expansion brings you very close to the approximate value that we know by other methods. And then the same ideas can be applied to this ON model. So have a lambda phi to the 4, but now have n scalar fields instead of 1 scalar field. And then in those ON models, I have 2 approximation schemes. I have a large n and small epsilon. And in principle, you can see whether tuning both of the parameters small, I get compatible answers. So I can be in 3 dimensions exactly at large n, find some approximate answer. Then I can be at 3.99 dimensions at finite n, find some answers like this, put epsilon to 1, and ask whether I agree with the large n. And all of these things lead consistent results, meaning that you are within some accuracy of order a percent or 2 or 5, you'll get the same answer. Which gives you confidence that your assumption of the existence of this CFT is actually true. Okay. So now, so everything I said in the past 15 minutes or so was for this bosonic models with scalar fields only. But our interest here is in supersymmetric models. So interestingly enough, this epsilon expansion was not well studied in the context of theories, not so well studied in the context of theories with both spin 0 and spin 1/2 fields. And really, there's no fundamental reason to not do it. This will be called emergent supersymmetry. So, take a theory that has 1 complex boson, scalar, and 1 complex spin 1/2 fermion. This is the field content of our Wess-Zumino model. Assume that the interactions assume that you have canonical kinetic terms, and then the interaction is specified by the following action or Lagrangian. So this is the conjugate of this. Okay, so I'm starting with this model, which has no supersymmetry whatsoever, okay? Again, I'm choosing the masses to be 0. just like in lambda phi to the fourth, I chose the masses to be 0. And then I want to study this theory in the 4 minus epsilon expansion. Again, doing loops and diagrams, the same story, but now I have two scalars, because it's a complex one, and then I have two fermions. And for some reason, this hasn't been done too accurately until recently. And so what happens, I'm not going to give you any of the details, I will draw a picture. What happens in this story is the following. So I have an RG flow. So the couplings evolve as a function of energy. So I have to compute two beta functions here, right? And see what their signs. I mean, it's again the flow of a vector field on the plane is what I have to study. So when the couplings vanish, I have a Gaussian or free, a Gaussian fixed point or a free CFT. This happens at high energies. So I'm in less than 4 dimensions, okay? So I'm in some d less than 4 and epsilon much more than 1. So this picture is rigorously derived using perturbation theory up to 3 loops. So it is not some imagination. There's actually detailed numbers behind it. So it's okay. You find a fixed point here, and you find a fixed point somewhere here. So you find 3 fixed points, 3 values of lambda and h for which the beta functions vanish. Okay, so this fixed point is at some value of lambda and h is equal to 0. So this point is 0, 0. This point is some lambda star 0. And this point is some lambda tilde and h tilde non-zero. Okay. Notably, this point is at, I didn't write it down. Now I have to worry about, I think it's at up to factors of order 1, lambda tilde is equal to h tilde. It is the value such that supersymmetry, such that this action actually has SUSY. Okay, so these are the fixed points, which is the first thing that you study when you have a system of differential equations, and then you should study whether they're attractive or repulsive. So this one is completely repulsive, meaning that, so the arrow indicates what happens at low energies. At low energies, you want to be away from this point. This one is attractive. This one is completely attractive. And then, this one is attractive if h is equal to 0. But if h is slightly non-zero, these lines curve. So you have these RG flows. And also from here. So in the direction of h, this is actually a repulsive fixed point. Which means that in the UV, at high energies, even if you have a tiny bit of the coupling h, it's going to grow and grow and grow in the infrared, and it's going to push you in this direction. So any tiny interaction in your system that induces such a coupling at high energies will be dominating the low energy physics. This is the story that happens. So this guy, and again, I want to really emphasize this point. You didn't build supersymmetry in. What you built in is the degrees of freedom that you have enough, that you have equal degrees of freedom between the bosons and the fermions. But the interactions are completely general, renormalizable, and supersymmetry just emerged at low energies. I didn't have it anywhere here in the middle of this RG flow. This CFT is, by the way, what's called the O2 model. It's like this this critical, lambda 5 to the fourth with two scalars instead of one scalar. This appears in physics in liquid helium. There is a critical point. So this is a thing that can be measured in the lab. This is obviously something that can be measured in the lab. It's the harmonic oscillator. And so, well, at this point, you should ask yourself. This is in some sense, so if I have some system that has two scalars and two fermions without a mass, it's gonna flow here. No question about this. So this was emphasized in 2013 by actually Smetter people. So there's a paper that was actually published in Science, of all places. So this is actually Science, because the journal is called Science. So you can't argue with that. So I encourage you to read about this. So again, this is a strong indicator from using RG in philosophy that supersymmetry in some systems should emerge at low energies. And they have a discussion of what kind of experimentally realizable systems can actually lead to this picture. A final comment, maybe before we go to lunch, is that I didn't talk a lot about three-dimensional n=1 theories. The reason being is that with this little supersymmetry, this is the minimal amount of supersymmetry, I don't have the power of holomorphy. No Zybergology available. And so really some of these exact things that I was claiming do not happen. However, in this context, in this condensed matter-ish kind of context, this is actually the theory that can arise from one real scalar and one fermion. So this is actually a simpler model to be looking at, and you can do this on 4 minus epsilon expansion for this theory. It's basically the same interaction with real fields. Okay? And it's exactly the same picture that happens. So this is not some accident because you had n=2 supersymmetry somewhere or something like that. No, this is whenever you have, so you have a Gaussian, this is now really the Ising model. And this is again some lambda and some h. Lambda is the 5 to the fourth coupling, and h is the Yukawa coupling, and you again find some other critical point. And again, this is repulsive, so it brings you here, and so on. So this is the critical West-Zumino model with n=1 supersymmetry. This one also probably deserves the name the supersymmetric Ising model, because it really is the thing that if you add one fermion with the Yukawa coupling to the Ising model, you will be pushed away from the Ising model, and this will be the dominant IR physics. So if you have boiling water with fermions, that should be the physics. Yeah, and in this theory, unfortunately, these exact tools that I mentioned, this supersymmetric localization story, is not available, but the conformal bootstrap is actually available, and people have studied this theory also with those tools. And of course, this is a picture, again, up to 3 loops in the 4 minus epsilon expansion. So the epsilon expansion is, in a sense, always available, even if you don't have supersymmetry. Okay, I think here is probably, for me, a natural place to stop and maybe ask you if you have any questions. Yes? Very good.
Because I expect that the list is
Yes.
equal to minus 1 equal to the one for the coupling transformation.
So the statement is actually very strong. So I will put another reference here. Again, condensed matter people did this. So in this paper, I think they focus on this model here with n equals 1 supersymmetry. But what they did is total violence. Their kinetic terms were not Lorentz invariant. So they studied kinetic terms of the bizarre type where you have things like dt phi, coefficient ct, plus dx phi, coefficient cx, plus dy phi, coefficient dy. And allowed for all kinds of quartic and cubic interactions, like what you're saying. So at this point, at high energies, you have completely broken also Lorentz invariance, which is something a condensed matter person would like, actually, right? And so you have many more couplings to worry about, many more diagrams that you usually don't see in a particle physics-oriented quantum field theory book because such things we don't look at, right? And what happens is that the RG flow is such that it pushes the couplings to be equal. So Lorentz invariance emerges, conformal invariance emerges, and supersymmetry emerges. So it's really, once you see the calculation, you should start believing this crap. Because, who ordered that, right? Yes, so indeed, you should be asking how finely tuned is that, and the fine-tuning here is only the mass terms. That's only fine-tuning. Which is, anyway, what, as I mentioned a number of times, is what we do for the Ising model anyway. Yes, other questions? No, okay. Good, let's have lunch.